Good day everyone. Let's talk about prime numbers and their discovery section, the Sieve of Eratosthenes. Before we begin, this presentation will guide us through one of the earliest mathematical algorithms, the Sieve of Eratosthenes. It connects history, philosophy, and mathematics in one topic. You see how ancient thinkers organized numbers and discovered structure long before computers. Prime numbers are integers greater than 1 that have only two divisors, 1 and themselves. They are the building blocks of all natural numbers because according to the fundamental theorem of arithmetic, every integer greater than 1 can be written uniquely as a product of prime numbers. One early and systematic way of finding primes is the Sieve of Eratosthenes, created by Eratosthenes of Sieve, who was also known for his achievements in geography and astronomy, including his remarkably accurate calculation of Earth's circumference. His sieve demonstrates an early form of algorithmic step-by-step problem solving. The slide defines prime numbers and why they matter. Prime numbers are special because they cannot be broken down further. They have no other divisors except 1 and themselves. They are the foundation of all natural numbers because every number greater than 1 can be written as a product of primes. This is the fundamental theorem of arithmetic. So, primes are like the atoms of arithmetic. Without them, numbers lost structure. The slide also introduces Eratosthenes, who created a clever method to systematically separate prime numbers from composite ones. What impressive here is that he did this thousands of years ago, without calculators or computers, just pure logic and observation. Let's talk about historical context. Eratosthenes, who lived during the intellectual rich Hellenistic period, contributed greatly to both geography and mathematics. His Sieve of Eratosthenes was more than just a method for finding primes. Show an early desire to bring order and structure to numbers. By systematically eliminating composite numbers, his method foreshadowed the algorithmic process that modern mathematics relies on today. This slide places Eratosthenes in history. He lived during the Hellenistic period, a time full of learning, exploration, and discoveries. Scholars were curious, motivated, and passionate about understanding the world. Eratosthenes wasn't only a mathematician. He was a geographer, astronomer, philosopher, poet, and the chief librarian of the Library of Alexandria. Like a Renaissance man, someone who can do many things, the Sieve of Eratosthenes wasn't just a math trick. It reflected the mindset of his era. Organize knowledge, find patterns, explain the world logically. It shows an early desire to create structure out of something that looks random like numbers. Let's talk about philosophical perspective. The Sieve of Eratosthenes reflects a philosophical search for purity and simplicity in numbers. Since prime numbers cannot be divided except by 1 and themselves, the Sieve's systematic removal of multiples isolates these basic numerical building blocks. It also shows how order can arise from chaos. Although primes appear irregularly among the natural numbers, the Sieve reveals an underlying structure that is essential to arithmetic and mathematics. This slide looks at the deeper meaning behind the method. Prime numbers represent purity. They are indivisible. When you remove all multiples, only the pure primes remain. The Sieve mimics a philosophical process. You remove noise, you eliminate distractions, you reveal truth. Even though primes appear irregular when you scan a list of numbers, the Sieve reveals underlying structure. Kind of like life sometimes. When you remove unnecessary things, the important ones appear. Mathematics teaches us that even in chaos, there can be order. Next is the Sieve algorithm. The sieve operates on a simple principle: eliminate all composite numbers systematically to leave behind the primes. Formally, the steps are: list all integers from 2 to a given limit n. Number 2, select the first unmarked number in the list. It is prime. Number 3, cross out all multiples of p greater than p. The number 4, move to the next unmarked number and repeat step 3. The number 5, continue this process until all numbers up to square root of n have been processed. Number 6, the remaining unmarked numbers are all primes less than or equal to n. This slide explains the step-by-step method. The amazing thing is how simple yet powerful it is. Here's the idea behind the algorithm. You start with a list of numbers. The first numbers is automatically prime. They can cross out every numbers that is a multiple of that prime. This continues until you reach the square root of your upper limit, which mathematically guarantees all composites have been removed. The method is systematic and logical. That's why it's considered one of the earliest algorithms, a clear process with a guaranteed result.
Very simple and very intelligent.
Remark, only numbers up to square root of n need to be considered because any composite number larger than must have a prime factor less than or equal to square root of n.
Let's talk about illustrative example. Primes less than or equal to 50. We begin with the list of numbers from 2 to 50. The first prime number is 2. Cross out all the multiples of 2 such as 4, 6, 8, 10, 12, and so on up to 50. The next prime number is 3. Cross out the multiples of 3 like 6, 9, 12, 15, 18, and so on up to 48. Then we move to the prime number 5. Cross out all the multiples of 5 such as 10, 15, 20, 25, 30, up to 50. Next is the prime number 7. Cross out its multiples 14, 21, 28, 35, 42, and 49. This slide visualizes how the sieve works in practice. You list numbers from 2 to 50, then remove all multiples of 2, then 3, then 5, then 7. What's left are the prime numbers. The example shows the mechanical elegance of the method. From something that looks messy, like random numbers, you need up with a clean set of primes. This demonstrates how the sieve transforms confusion into clarity. It's like organizing a cluttered room after removing unnecessary items. You can clearly see what's important. Remaining primes: 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47. This example demonstrates the mechanical elegance of the sieve transforming a seemingly arbitrary list of numbers into a collection of pure primes. This table shows the steps of the sieve of Eratosthenes, a method used to find all prime numbers up to 30. Each row shows what we do in this step, which numbers remain unmarked, and which numbers we cross out. We begin by listing all the numbers from 2 up to 30. At this point, no numbers are crossed out yet. We identify 2 as the first prime number. Then we cross out all of it is multiples because multiples of 2 cannot be prime. So remaining numbers 2, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23, 25, 27, 29. Cross out 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Next, we take the next unmarked number 3 and mark it as prime. Then, we cross out all multiples of 3 that are still in the list. Remaining numbers 2, 3, 5, 7, 11, 13, 17, 19, 23, 25, 29. Cross out 6, 9, 12, 15, 18, 21, 24, 27, and 30. The next unmarked number is 5, so we mark it as prime. We then cross out all multiples of 5. Remaining numbers 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. Cross out 10, 15, 20, 25, and 30. The next unmarked number is 7, so we mark it as prime. Then we cross out its multiples. Remaining numbers 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. Cross out 14, 21, and 28. We stop the process when we reach the square root of 30. All the numbers that remain unmarked at this point are prime numbers. Prime numbers 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. This slide gives a smaller example so learners can easily follow. Using the same steps on number 1 to 30, we get the list of primes. This reinforces the idea that the sieve works no matter what range you use, small or large, consistent, predictable, and reliable. Theoretical insights. The sieve is more than a computational tool. It has conceptual significance. It provides a deterministic procedure to generate primes. It exemplifies algorithmic efficiency. Time complexity is 0 and log in, making it practical for moderate ranges of n. It underscores the fundamental role of primes in number theory and cryptography, as primes underpin modern encryption algorithms. Mathematically, the sieve illustrates the structure and order exists within the natural numbers, even when patterns appear irregular at first glance. This slide explains why the sieve matters beyond basic math. Here are the key points. It's deterministic, meaning it always gives the same output for the same input. Next is efficient. Its time complexity 0 and multiplied by the logarithm of n. Is very fast for moderate values of n. It is foundational in number theory and cryptography. Prime numbers are essential in modern encryption systems like RSA, which protect passwords, banking data, and online communication. Imagine an algorithm invented more than 2,000 years ago. It still helps secure the digital world today. That's how powerful prime numbers are. The Sieve of Eratosthenes represents the intersection of history, philosophy, and mathematics. Invented over 2 millennia ago, it remains a cornerstone in number theory. Inventor, Eratosthenes of Cyrene. Purpose, identify all primes less than equal n. Method, repeated elimination of multiples. Significance, reveals the fundamental structure of numbers and demonstrates algorithmic reasoning. The conclusion ties everything together. The sieve is not just a mathematics tool. It symbolizes historical curiosity, philosophical depth, mathematical structure, algorithmic thinking, and modern-day relevance. It shows that ancient knowledge can still influence today's technology. That's why it's timeless, simple yet profound. As we end this report, I just want to remind everyone, learning isn't about perfection, it's about progress. Thank you.